the idea behind this talk is to try to associate our understanding of the sky and of the universe with our own existence. So one of the hardest things to teach when you teach astronomy is that it's not just stuff out there, that we are part of the universe. You know, our matter was created in stars that exploded and spread back throughout the universe. And so one of the things that we have to try to do when we learn about astronomy is to try to understand how does it connect with us. So that's the origin of the title, Universe and You. And then the other part of it is the title is inverse, because as I've gotten older and crazier, I'm less inhibited. I basically have written books, little poems for my grandchildren, and now I use them for my instruction when I'm teaching my classes. And so what I'm going to try to do is use a few of these poems to kind of illuminate some of the most interesting things about our universe. But it's very, very flexible about where we go, what track we follow. So I'm going to ask for you guys to give me some guidance about what part of the potential different tracks we can take. One of the particular poems is about that thing right there, that big yellow thing. It's our sun. And so there's a poem called The Star of Our Life and the Life of Our Star. And the idea behind this poem is you read the poem, and then in each line and stanza of the poem, there's science. And so rather than have, you know how they say a spoonful of sugar makes the medicine go down? That's the way I feel about, you know, teaching science. By making it more poetic, as it were, you can get, you know, further. And then there's also a poem about the Earth itself. And then there's a couple of poems. This is a poem I wrote for my granddaughter. She's now 5 years old. Actually, she'll be 6 in April, or end of March. And then my second granddaughter, there's a poem about the scales of the universe called 26 Jelly Beans. And I've only been able to publish these so far as photo books, you know, that I made, but I do have copies if anybody's interested. And I think the MtCuba here itself has copies. And then the other thing, for anybody here who's got a little bit of technical background, basically some math, I've written a textbook for the course I'm teaching right now, Fundamentals of Astrophysics. And it's for a textbook. I'm very proud of this. I worked very hard with the publisher. It's only $45, which for a textbook, if you know, is really cheap for the soft cover. Yeah, so that might sound like a lot for a book, but for a textbook, you know, the students are always saying, well, some of the textbooks that we've used in my class have been $150, crazy stuff like that. Anyway, some of the people in the class here have taken my courses, so you know, there are gluttons for punishment, because here they are, they're still here. Hi, welcome, thanks for coming. So anyway, the bottom line here is that if you ever have any questions about astronomy, one of the things that I try to do, and thanks to the fact that I get supported, well, I get paid to be a university professor, but I also get money from NASA and NSF, is I always try to be a resource for anybody who has questions about astronomy. And I don't know everything about astronomy, but I know a fair amount about the basics. And so if you have any questions. So for example, right, what's in the news right now? Have anybody heard the big exciting thing in the news?
The meteor in Texas.
I'm sorry?
Is it the meteor?
No. It's even more profound. There's a new theory that there's something called dark energy that's making the universe expand faster and accelerating. Well, there's a new theory or a new idea that basically this dark energy comes from black holes. And that's all the astronomers are all kind of a Twitter, as it were. Okay, anyway, but what we're going to do tonight is the first thing I want to do is try to connect us with the universe. And so you think about us, if I put my hands up, like if there's a touchdown, the referee says it's a touchdown, well, the distance between his two hands, the referee, his or her, now I guess they're female referees now, is about 1 meter. A meter is about a little bit more than a yard, and it's the characteristic scale of our life. We are a little bit more, most of us are about 1.5 meters, maybe some really tall people are 2 meters, but basically that sets the scale of human beings. So now the question is, how do we go from there? Well, if we took a bunch of people, everybody in this class, in this room, and held hands, 10 of them, that would make 10 meters, which is about the difference, how far you have to go to get a first down in football, right? And then, of course, you took 100 people, you would have 100 meters, which is about the length of a football field. So where did this idea of a meter come from? Well, it's the metric unit of length, which we don't use here in the US, but everybody else in the world does. And how did it originally get defined? Well, it was originally defined as 1/10,000,000th of the distance from the pole of the Earth to the equator. So if you ever forget how big the Earth is, all you gotta do is remember that it was originally defined to define the meter, 10 million meters. So if we went all the way around the Earth, right? Well, to go around a circle, you have 4 of these, so it'll be 40,000 meters, or I'm sorry, 40 million meters, or 40,000 kilometers. So that's the circumference of the Earth, 40,000 kilometers. If you ever forget, that's one way to remember. Now, the whole point about this is that when we start going into astronomy and anything that's bigger than us, we start having to worry about huge scales. So in this case, we have 10 million meters. And so what astronomers, of course, do is they say, well, let's not worry about the number of zeros. It gets boring after a while. Just count the number of zeros and then just raise it to 10 to that power. So 10 to the 7th meters is 10 million kilometers, 10 million meters. So now we all have experience with the Earth. We've flown to Europe or Iceland or whatever, right? And we all have a feeling for how big the Earth is. It's 10 to the 7, 10 million times bigger than us. But the key here is, so we can think about it as kind of, here we are on this scale, and there's 10 rungs of this power of 10 ladder, 7 rungs of this power of 10 ladder to get you to the Earth. So that connects us to this body called the Earth, which we're familiar with since we've traveled around it. We know how long it takes to travel from East Coast to West Coast by car. It takes several days. And that's maybe a fraction of the Earth's scale. So it's on the order of the scale of the Earth. But the key thing is that the Earth is our transition between us and the universe because it's one of the planets, right? The biggest planet in the solar system is Jupiter. And it turns out to be about 10 times bigger than Earth. And so that's just another power rung in the ladder, 10 to the 8th meters. And then turns out the sun is about 10 times bigger than Jupiter. So if you took the sun to Jupiter across, it would be like 10 of them. If you put the Earth, you'd have 100 Earths going across the sun. That's how big that's why when you look at this picture, look at the Earth, it's like that third thing from the sun. Look at how tiny it is by comparison. It's 100 of those can go across the Earth, right? So here we are. We're now at our star. That is the star that we depend on. It's 10 times bigger than Jupiter, 10 times, which is bigger than 10 times. So it's 10 to the 9 meters, or a billion meters, or a million kilometers. That's the size. But wait a minute, how far away is the sun? Well, the sun turns out, you can't do it on this diagram, but if you took the sun and put it side by side 100 times, 100 diameters, that would be the distance to the sun. The sun is 100 times further away than its diameter, than its physical size. So there we go. Now we're up to the size between the distance between the Earth and the sun, and that's called an AU, an astronomical unit. That's the sort of basic unit of distance in astronomy. So now that's 10 to the 11, or 100 billion meters, or 100 million kilometers. It's actually 150, but we're just doing orders of magnitude here. Now, where we go from there? How far away is the nearest star besides the sun? Well, it turns out we have to add 5 powers of 10 to the ladder, 100,000 times further away. Why are stars so dim compared to the sun? They're all some of them are brighter than the sun intrinsically, some of them are dimmer, but on the average, the reason that they're so dim to us is that they're so far away. The nearest star is 100,000 times further away than the sun. Now that's a distance which we sometimes we call that distances of order. The nearest star is 4 light years away. The sun is about 4 light minutes away. It takes about 8 minutes for light from the sun to get to us. It takes years for the light from the nearest star to get to us. So here we are. Now it turns out that there's a, so that's 10 to the 16 meters, 16 powers, 16 rungs the ladder is the distance to the nearest star. So what about the galaxy that we live in? Well, that turns out to be 100,000 times bigger than the distance between the stars. So there are about a few hundred billion stars in our Milky Way galaxy, but the galaxy itself is about 100,000 light years across, 10 to the 5 times bigger, another power of 10 to the 5. Where do we go from there? Well, the universe itself might be infinite, but we can only see the part where light could have reached us since the Big Bang. The universe is about a little more than 10 billion years old, about 13.8 billion years old. That means during that time, there can only have been about 10 billion, a little bit more than 10 billion light years. That's another 5 powers of 10. So the universe itself is now another power of 10 there. So when you add all these things up, that's like 10 to the 7 plus 1 plus 1, that's 9. There's 11, 16, 21, 26. 26 powers of 10. By multiplying 10, 26 times, we go from us to the whole universe. Now, we can go on from there, but powers of 10 are very powerful, but it's easy to get lost in them. So for instance, we could imagine that you're driving from one town, one city to another city, and every mile there's a mile marker. But do you ever mark off every mile, or do you mark off the miles between the big things, the big cities? Well, the same way, this is identifying the key markers for these mile markers of the universe. And so what do we want to do? Let's try to remember them. Well, we have 711-2555. That's like a telephone number. So if you can remember somebody's telephone number, 7-digit telephone number, you can remember how big the universe is compared to us. Okay, so here we go. 711, it's like the prefix number, 2555. You can remember everything between us and the universe. Okay, so now where do we go from here? This is where we get to decide what do you want to do next? So what we could do, we could, for instance, read the children's book, 26 Jelly Beans to Ginormity, in which the little girl asks her grandpa, what's the biggest thing there is? And he says, well, it's hard to explain, but I can show you with these magic jelly beans. Every jelly bean will make you 10 times bigger. And so after she eats different numbers of jelly beans, she's as big as the sun, she's as big as the distance to the nearest star, she's as big as the universe after 26 jelly beans. And so that's the children's story that I've written for my second granddaughter. And now I first got started writing these poems from my first granddaughter, Big Stars for Little Star. I study these stars that are very, very massive. And then I wrote this poem about big stars for little star, which brings in. But that led me to writing things for my classes, not quite children's books. A poem about the Earth and a poem about our sun. So we can go any one of these, or we could just go on a little bit further and then come back to the poems. It all depends on what you guys want and what you want to learn about. So let me just sort of say that if we now go down from us to the smaller scales, well, the smallest things, our bodies are made up of billions and billions of cells, and they're all about 10 micrometers, or 10 to the minus 5 as big as us. So our cells are about 5 powers of 10 lower. And then the atoms are about 5 powers of 10 smaller than individual cells. And then the nucleus, which is the core of the atom, is 100,000 times smaller at 5 powers of 10. So the point is that we can go down from here to the size of an atomic nucleus, and all we have to do is add a country code, or area code, 555-711-255. That takes us all the way from us. Now that you had 15 to 26, that's 41 powers of 10. The nucleus to the size of the universe is 41 powers, 41 steps in this ladder. But is that as far as it goes? Well, no, because there's things that are smaller than atomic nuclei. They get detected in these hard high energy particle detectors, because in order to get to smaller and smaller scales, you have to go to higher and higher energies. And the smallest scale we can imagine is called the Planck length. It's the length over which an individual elementary particle would become a black hole. It's where quantum physics, the basic physics of microscopic matter, and general relativity, Einstein's theory of gravity, merge. And that's 20 powers of 10, smaller than the nucleus. So all you have to do now is add an area code. That turns out to be a country code. That turns out to be the country code for Egypt. All right, so there you go. Now it's 61 powers from the tiniest scale where our physics breaks down to the size of the universe, 61 powers of 10. Now, we can also do this with other things like time. Most of us live on a heartbeat, which is about a second. But a second is a little bit more than 100,000. A day is a little bit more than 100,000 seconds. And then there are 365. It turns out that 10 to the 7.5 power seconds is one year. And then, of course, we live for about 100 years at most, if we're lucky. And then civilization's been around for about 100 lifetimes. And then our species have been around 100 times longer than that. And then the dinosaurs were around 100 times longer than that. And then we get to the Big Bang. So there you go. All these powers of 10 can organize time for you as well. Now, that's only interesting if you're trying to, you can also do the same thing with speed. It turns out if I'm walking right now, I'm going about 1 billionth of the speed of light. But as you go up and ride a bicycle, you go 10 times faster, car 10 times faster, airplane, moon, Apollo astronauts were going this speed. And then you have the sun, something I call, what I study is stellar winds, supernova, and then light itself. That's the fastest speed. And there's Einstein at the traffic cop saying you can't go any faster. Right? Okay, so that's kind of the basic outline. So next thing we need to do is now just decide what do we want to look at of here next. So I would say it's up to you guys, but maybe since we're all here on Earth, let's do a poem about the Earth and find out about its place in the universe. Okay, so let me do that. Okay, so this is the poem about Earth as a strong astronomical object. And I call it Our Oasis in Space. Okay, and all these poems start with, this is a ball. This is a ball, the sphere of our birth. It's home to us all, our blue planet Earth. It spins once a day on an axis with tilt. Sun towards or away is how seasons are built. When the northern part of the Earth is pointing towards the sun, we have summer. And when it's the other way around, we have winter. That's how seasons are built. As the Earth goes around the sun, that's how we have seasons. As it orbits our star at a distance that's home, not too near, not too far, in the Goldilocks zone. Just like Goldilocks, got one thing is too hard, one thing is too soft. We live at just the right place. Because Mars freezes in ice. Venus bakes in dry steam, dry meaning here carbon dioxide. But here it's so nice, liquid water can stream. But it wasn't so mild 4 billion years past, 4.5 billion years past. When together rocks piled our molten planet to cast. The early part of the solar system, our Earth was formed from material in the disk going around the sun. In a final big crash, a companion was hewn from the ash of the smash that formed to our moon. Our moon was formed when another body hit the Earth. Shortly after it was formed, by the time the iron had already settled out, hit the Earth and picked off a bunch of material from the Earth's mantle, and that made the moon. And we know this because when the Apollo astronauts came back, the isotopic signatures of the moon dust is the same as the Earth's mantle. So we know that the moon was once part of the Earth. It's one of the great discoveries from Apollo, by the way. This made a big dent, but with gravity's snare, the hot gas that did vent trapped a layer of air. So Earth's atmosphere came from venting of volcanoes and so forth, with gravity holding the atmosphere down onto the Earth. Even after this slaughter, icy bodies hit still, adding ever more water, deep caverns to fill. So this was the origin of our Earth's oceans, the bodies, the icy bodies that hit the Earth after it was formed. The oceans of blue came to cover Earth's surface, to give it its hue and salve for its purpose. So this is how the oceans were formed. But of course, the oceans are really key. For this was the soup that cooked the first gels, then in time came to group into billions of cells. Inside the ocean, cells were little spheres formed, eventually became cells, they grouped together, and they made things like jellyfish and so forth. These crawled onto land once they grew a hard spine to walk upright and stand, then evolve to our mind. So treasure this home, life's oasis in space, but let your gaze skyward roam, its past faces trace. So how do we know all this about the Earth? Well, partly by studying the Earth in context with other bodies in the solar system and with other bodies, other planets that we are discovering by various telescopes. So there's a whole direction here where we could go and talk about planets around other stars and whether they can have life or whether they're in the Goldilocks zone, okay? And we could go back, and one of the most beautiful quotes I've ever heard in astronomy was when Carl Sagan had them take a picture of Earth from Voyager as it was leaving the solar system. And there's a little pale blue dot. And he talks about, on this pale blue dot, everybody who ever knew, every person, every lover, every tyrant, everybody, every living being lived on that little pale blue dot. And here we are sitting in the universe, and we're so special because we have this thing called life. And it was all just because of all these accidents that the moon formed, and that stabilized the Earth's orbit and stabilized the Earth's rotation. And there's all kinds of things we can go into here. And so that's just kind of the first introduction. And we can either talk some more about that if you want to ask some questions, or we could go on to maybe a poem about the sun. What do you want to do? What are your choices? Anybody want to ask any questions about Earth's formation, its history, and why is it the way it is? Nope. Okay. Let's go on then. Yeah.
You said the oceans were created by ice hitting the Earth.
Rocky, icy asteroids. So when you look out in the solar system, we've now, with our spacecrafts, been able to measure the kind of isotopic abundances of ices in different places in the solar system. And the ones that match the best are the asteroids that are just beyond Mars. And so what we think happens is that these asteroids in the early solar system was much more chaotic. And these asteroids came flying into the inner solar system. When the Earth formed, because of this giant collision with a Mars-sized body to form the moon, it was pretty barren. It was pretty barren. It's very, very hot. Most of the water, which is very volatile, was cooked off. And so we think that most of the water in our Earth today came from these comets, these not comets, but asteroids that were impacting the Earth during the early solar system. And so we're lucky that we have all this that happened, because we wouldn't have the oceans and we wouldn't have the water. Okay. Anybody else? Yeah, go ahead. Yeah, so what happened is that the early solar system was very chaotic. There were lots of bodies that were colliding together and sticking together. And in the final stages of the solar system, every planet had to clear its orbit. This is one of the reasons why Pluto was demoted, because supposedly it didn't clear its orbit. But every planet would clear its orbit, get rid of all the debris in that orbit. What happened with Earth is that it pretty much was all formed. For example, the heaviest stuff, iron, already had sunk to the core. Then this body that was the size of Mars, we call it Theia, hit the Earth and knocked off a whole bunch of material from the Earth's mantle and crust. That material then coagulated into the moon and became the moon and orbited. And we can see this today because when we measure the isotopic signatures of material on the moon, it's identical, like a matched fingerprint with what we see in the Earth today, and the Earth mantle. What's missing from the moon is much iron, because the Earth had already had all its iron sink to the center. So only the material in the outer part of the Earth got knocked off. So the moon doesn't have very much iron. Well, this is very special. Our moon is almost the same. It's only a quarter. It's a quarter the size of the Earth. If you look at the moons of Jupiter, they have 60 or 70 moons. They are tiny compared to the planet. They formed as sort of mini solar systems. The way the sun, what happened is when the material collapsed to make the sun, there was some material that was spinning too fast, and so it couldn't fall into the middle. And so it went into orbit around the sun and eventually became the planets. But inside, when Jupiter formed, it also had the same process where material tried to collapse to Jupiter, a lot of material was left behind, and it made a bunch of moons. The four biggest moons are called the Galilean moons. They're about the size of our moon. But the big difference is that Earth's moon was formed by this collision, this very crazy random event, whereas the moon of Jupiter was kind of just formed by a very regular process, which is just when you collapse something, you can't always have it all collapse in the middle. Some material always falls behind. You and I are here today, as opposed to not being a part of the few of the atoms that are inside the sun, because our matter in the early solar system was spinning too fast and couldn't fall into the sun. Yeah.
So if the moon was part of the Earth, why is there no life?
Why is there no night?
Life.
Well, because it's too small to hold back the atmosphere. Icy bodies hit the moon as well, but because there's no atmosphere, all that water escaped into space, except we now know that some of the material in the poles of the moon got in perpetual shadow in the craters. And so we now know that there is some ice water on the moon. And water is a very important thing if you're going to go explore space, because water gets something you drink. You can also use it to grow things, but you can also use it as rocket fuel by splitting the hydrogen and oxygen apart and then allowing it to come back together to make rocket fuel. So finding water on the moon is a really big deal. And there's going to be a big competition to see who gets to that water first. China's ready to go. The US is going to go. There's not an unlimited amount. There's much less than on the Earth, but there's a lot of water. I think it's estimated to be something like a few times the amount of water in the Great Lakes is on the polar hidden on the moon. Yeah.
Just thinking about the huge volume of it.
Right.
It seems extraordinary. I don't understand the physics and chemistry enough, but to think of anything other than what you outlined, it seems extraordinary that so much being come from outer space, really.
Well,
and I just wonder whether the early is capable of creating its own.
Well, it certainly there was. See, when you look at the abundance of elements in the universe, the most abundant element is hydrogen. Then comes helium. Then the next most abundant element is carbon and oxygen. And that has to do with synthesis of elements in the sides of stars, which then explode. Carbon and oxygen are the two fundamental elements that make us possible, because all of our carbohydrates, those are all the long molecules that make up our bodies. The oxygen, of course, we breathe to sort of metabolize those carbohydrates as our fuel. So, all right, if you have oxygen and hydrogen, you're going to make a lot of water. So there's been a lot of water in the solar system. The problem is in the inner solar system, it was too hot to make solid, and so a lot of it just escaped into space. And But there probably was a fair amount of water in the original Earth, or at least available. But then this comet came, this asteroid, I mean, this Theia, Mars-sized body came and just knocked a lot of that stuff. And they got so hot that a lot of that water just escaped. So after the Earth was kind of dry, and then it had to get resupplied with water by the asteroids. Now, one of the questions is not why is there so much water on Earth? Why isn't there more water on Earth? Why, you know, the Kevin Costner movie, Waterworld, where there, you know, well, if you really melted all the water, you would have a lot of water on Earth. And so there are, when we look up into space and we see now new planets, some of them we think are basically just cover the water, and there isn't no dry land. And that's because they didn't have a Theia come along and knock it off and get rid of a lot of their water, and then have to get resupplied. So there's all kinds, it's like leads that we could go on forever about all the implications of this kind of poem. This every stanza of this poem can be written. You can write a paper about it. You can write a term paper about it, right? All right. And so anyway, so let's go on and let's do one more about the sun, and then we'll come back and we can just talk about whatever you guys want to talk about. Let's do one more, okay? Star of Our Life. Okay, so the idea behind this poem is that to talk about our sun, because our sun is a star, but it's very important to us because it gives us all the energy. So again, this is a ball of hot glowing gas. We all live in its thrall. This is a ball of a hot glowing one. We all live in its thrall. It's our very own sun. It lights up our sky and hides in our night, masking stars that seem shy until it sinks out of sight. But itself is a star, just looks big and shiny because it's nowhere as far as the stars that seem tiny. The idea is that the only reason that the sun is so remarkable is that it's much, much closer than any of the stars, as we learned about in the first section. It's just the right place to keep us all warm from the coldness of space out of which it did form. The sun formed from a giant clouds that collapsed into the, to burn this up. That was eons before, when a cold, dusty cloud got compressed to a core within its own shroud. So the gravity of these interstellar clouds pulled the gas together and made the sun. Some of the material was spinning too fast, so it made the planets. But this is the way our sun formed, from a cold, about 4.7 billion years ago. From gravity's power, it started to glow. With each floor of its tower, core pressure did grow. So the idea here is that gravity, as the sun was collapsed together, the gravity that it was falling in, it's like if I drop something, it makes noise. That energy from dropping makes energy of sound. Well, when you have collapsed a cloud into space, it releases energy of gravity, and that heats up the sun. So the sun first started to shine just because it was because of gravity. But then the gravity compressed the core of the sun to very, very high pressure. And so what did that allow? The high pressure pushed atoms to fuse, turning some of their mass into power to use, like the burning of gas. So the sun became hot enough in its core to have nuclear fusion go on. And now that replenishes the energy that the sun's giving off. There are a bunch of these nuclear bombs going off in the center of the sun all the time. The light that is made from this fusion of matter by a chain of cascade to the surface to scatter. When you're inside the sun, the light has a really hard time getting out. It takes several thousand years, we learned about in my class, right, for the light to get out. And in the process, it goes from very, very high energy light, gamma rays, into visible light, or eyes. This is the source of our sun's steady shine. just half through its course after eons of time. So here's like the sun forming. This is kind of 8 billion years, as it were. And right now we're about right here. Eventually the sun will continue to grow, and then we'll see what's going to happen next. So it's just half through its lifetime, the sun right now. But when finally spent, or the hydrogen in the core, when the finally spent, our star will then morph, puffing outward to vent, from red giant to white dwarf. So the sun, when it finally runs out of fuel, it will puff up, it'll burn up the Earth, and then it'll eventually, a lot of the outer atmosphere of the sun will just fade into space. And what's left behind is a core, very, very hot core called the white dwarf. All we know will be gone, but that's far away. So be sure with each dawn to bask in the sun's day. A long time. I once gave a talk about this to my kids' elementary school when my kids were still in elementary school. And then the next day, I got a whole bunch of letters saying, I can't believe the sun is going to burn up the Earth someday. Right? Well, it's going to be 4.5 billion years from now. You don't have to worry about it. All we know will be gone, but that's far away. So be sure with each dawn to bask in sun's day. For over 4 billion years, it's been warming our Earth so that oceans of tears could evolve to your birth. So the idea here is that because the sun was so steady and has kept the Earth pretty warm for this time, kept the oceans mostly liquid during the whole time, there was time for this complex evolution, of cells to form all this matter. And then eventually, as we talked about in the last poem, this became the birth of life and us. And so we have this picture of, it's almost like from 2001, right? Where they have that child be born with the universe in back. But so what I find is remarkable is that the womb has the salty fluid in it, amniotic fluid. It's just simulating the ocean out of which our bodies were originally made. We're made of 65, 70% water because we were coming from the oceans ourselves. And I think this is an incredibly beautiful story about how it just all became possible, that everything was just right to make us possible. So that's kind of part of the whole universe in you theme of this presentation, is that we are not separate from the universe. It's not up there, but we are all active parts of it. We are part of how the universe has managed to develop into things that can contemplate itself, which I think is really remarkable.